Alright, let's continue with this problem. So in the last video, we have found a solution that seems to be efficient. I have now taken away all the print that I had before. So this is my current solution. It starts from this empty string to store our result. We have this variable k, which is the so let's go back to our example from last time. So if the number of rows is 5, the number of columns, which by number of columns I mean this part, this vertical part plus this diagonal part, and then the next column will be this vertical part plus this diagonal. So in each of this little section we have the number of rows, that's how many elements in this vertical part, and then the diagonal part will be number of rows minus 2 because we're taking away the edges. So that will be number of rows plus number of rows minus 2. That's why we have number of rows times 2 minus 2. So k is 8. In this case, we have 5 elements here, 3 elements, so 8. So each of these has 8 elements. And the remainder is how many is left over after all these complete sections. So each of these have 8, and then we have 7 left. Now that we're using 23 elements as an example, so we have 8, 8, and the 7 left. So that's the remainder. So we're calculating number of columns and remainder. And actually, I'm kind of surprised why this is not snake case, because it's Python convention to use snake cases for variable names. Okay. Anyways, so what this is doing is, since this will be dividing k cannot be 0, so when will k be 0? So if k is 0, the number of rows is 1, because k is that times 2 minus 2. So the only time k is 0 is if we're just doing one row. And think about it, if we're just doing one row, then we're just writing out this entire thing in one row, so then we can just return it right away. So now we've gone over this part. Okay, so we are iterating row by row. So start with row 1. Now we're gonna do this how many times? So we have this input, and the output will be the same length string, just in different orders. So we're gonna do this when it hasn't reached the same length. Or we could also actually just use when row is smaller than the number of rows. Since we're so, well, let's try that right away. Yeah, so that works, yes. So this is more clear. So we're starting with row 0, and we're gonna do this until we reach the last row. So, okay. So we actually do not need this either. I don't know what I was thinking earlier. Earlier I was thinking some other index that will go around like that. Okay, so I don't think we need that. So actually, let me see. For row in range, number of rows. Okay, better time as well. That's interesting. See, that's really good time. Okay, so we're in the middle of refactoring, so this is good. So now we get cleaner code. So we are iterating row from row 0 to the last row. So for row in range, number of rows. Okay, so if it's the first or the last row, then we don't have diagonal elements. So what do we do? Oh, now I'm seeing how I would be able to refactor a little bit more, because we are seeing same code here. Okay, let's see. So for first and last row, we don't need the diagonal elements. And what do? We have J goes from 0 to the number of columns -1. So in this case, we have number of column 2. So it's gonna go from 0 to 1. So now we are just writing out the 0, 8, 1, 9 to 10, these. So what it's gonna write is, we're in row 1, so it's gonna start with row 0, and J is 0 first, so that's S0, and then J is 1, so that is 1 times K. K is 8. Not 9. K is, let's just put it there so we have everything in one place. So K is 8, so it's S0 and S8. So how we came up with this whole logic, that's in the last video. So so that's all for this for loop. So we're writing S0 and S8, which is what we want. And now let's check if there is this remainder part. So if number of columns times K, so that's how many elements these are, plus row. So we have number of columns 2 times 8 is 16, so we have 16 elements for this entire part, and plus the row. So we're currently at row 1, but when we go later, let me look at later. Alright, so since we're only gonna do this row, okay, yeah, so that's correct. So when this is the case, so this part is to make sure that it doesn't go out of index, as we saw in the last video. Actually, let's see. If plus row, actually I'm not sure if we need this, but let me just try. Columns times K plus row, that shouldn't go over the length. Why does it? So number of columns times k, that would be 16 plus row. I'm thinking when it would go out of index, because we are still in the first and last row, and 2 times 8, so we have 16 plus row 4, because row can only go from 0 to 4, so that would just give us 20. So when would that go out of index? Okay, actually not sure. I have to think about that later. Okay, let's go over this first. So that is for the first and last row. And now okay, so this part is for all the rows in between with these diagonal elements. So we're first doing the same thing, we're adding these vertical elements, and then we want to add these diagonal elements for each of this little section. So for each of them, for each row, we only have that vertical element and one more diagonal element. So that's the vertical element, and this is the diagonal element, and where this part is the extra index that we have explained in the last video as well. So it will always be k minus 2 times row. So k is 8. Actually, if k is 8, if k is 8, row is 0, so this is plus 8. I'm thinking how I can combine this with that, since we do have this duplicate part. So if okay, let's see for J. What if we do something like this? If it's not the same, okay, if it's not the first row, okay, if it's not the first row and it's not last row, then we add this diagonal element. So that will go over, for each row that will go over this part. Okay. And now we are taking care of the remainder part again. So we want to So this is the vertical remainder part, and this is the diagonal remainder part. Okay. All right, let's first check if this works. Promising. Wrong answer, very interesting. Let's see. We are missing a, we are adding an extra D. How is that possible? Oh, right. Because this condition also needs to be in, so that condition is to make sure that we're not adding these extra diagonal elements to the first and last row, so that also needs to be in here. Oh, that was there. So if it's not the first or last row, then we might have this remainder diagonal elements. Okay, so that works. That works, but it doesn't seem to be as efficient. It is the same algorithm though. All right. So we have refactored quite a bit, so that's really good. It's progress. Now, it still doesn't look very clean to me. I keep getting distracted. I keep getting distracted by these messages that I have to check very soon. So let's try to finish it up quicker. We're going over all the rows. For each little column section, we are adding that, and then we do the remainder section. So I was also not sure in which case this would go over the length of the input, because the number of columns is a constant case, a constant row will not go outside of the number of rows. So I don't know when that would not be the case. I'm curious. Let's investigate. So this part is what I removed. Let's print this. And see how that is not. Okay. what this test case is. Okay, it's the same one. So 14, apparently A1 to 14. So for 3, we have K is 3 times 2 minus 2, so that is 4. K is 4. So number of columns is, so this is still 14. Okay, so 14 divided by 4. So number of columns is 3. Okay, so 3 times 4, 12, plus row. We are at, we want to see which row that is as well. Let's just add that. At row 2. Okay, what do we have now? Number of columns was 3. K was 4, so 12 plus row 2. Okay. Oh, I see. It just ran out of it. That's, I see. Yeah, for those cases, it actually does not go all the way down, like in this case, because in this case, it will go from row 0 to 4, so it will not cause this error, because it will go over all these rows and then do the corresponding ones. But for that case, we do not need, there is nothing there, so we need to stop. Okay, now we know why we need that. I think I probably understood that from the last video, but now I have forgotten that part. Okay, but it's okay. So this is to make sure that it does not start trying there. And if it's not the first row, it's not the last row. And I mean, there's a bunch of if. I could put this all in the same row. It doesn't look much better either. Well, well, this does not look good at all. That is a really good runtime though. Okay. Alright. Okay, I really need to check that. So we don't need to print that anymore. Okay, so we have refactored quite a bit. This looks okay to me now. Oh, it's been 25 minutes again. So let's do time and space analysis and then try to finish up this video. Time and space. So in this for loop, with the first for loop, we are iterating by each row. That would run the number of rows. And the second for loop, we are doing for each little column section. And inside, we are just doing constant operations, assigning, comparing, assigning, and calculating. So nothing that's not constant inside here. Okay, so the number of rows times for each row we are doing like this. So for the first row loop we are doing that, and then the second, the third. So for instance, for this row, we're coming here and we're gonna do this session, that's one round in this J for loop, and then this session, that's the second round in the J for loop, and that's it. Then we're out, and now we are just taking care of the remainder session. So for each row we are just gonna do these elements. So all in total, so many messages. So all in total, one sec, let me just turn this off for 1 second. Okay, sorry about that. So even though we are doing 2 for loops, we are actually just going over every single element in the inputs just once, getting that and retrieving it from where it needs to be and putting that into our output. So this whole algorithm will still be linear with respect to the number of elements in the input string. Now space, we are having some variables store constants, and we use this result to store the result. So other than the result string, which will be linear obviously, we are just using constant space because we're just using some variables. We're not using any data structure. So I think this solution is very efficient. It's linear time, constant space, if we're not counting the linear output in space. So it's pretty good. Do we have time to take a quick look at top solutions? All right, let's just do it really quickly. Let's do this Python linear solution. All right, let's just see very quickly. Oh, it looks very short. That's elegant. If we only have one row, or the number of rows is bigger, okay, then we just return right away. What do we have here? L is empty list times the number of rows. Okay, so list times the number of rows, index and step. For x in S, x in S. Okay, so for each character in this input string S, L index oh, okay, I see. So first it is putting in the first letters inside. Oh, I see. So it is constructing this whole structure. I see. It is constructing this entire structure. So for each row, it has this. So this is for each row. It starts empty, and then it adds up each character. So it adds the character in place like this. So for each character, it adds it like this. So first it adds this character to this position. If index is 0, okay, so index is actually the row here, I think. Let's see, if row is 0, if we add the first row, step is 1. What is step? This is not very good. It's not, it doesn't have any explanation. Okay. If it's the last row, step is -1. Okay. So index is then incremented with that step. Okay, we start out with index 0. We are at first row. So now we can go to second row. Okay. Oh, so step starts out with 1. Okay, I feel kind of stressed because I don't have much free time right now. But okay, let me just try this one more time quickly. Index 0, step is 1. So we start from index 0. Step is 1. Now index is 1. So next round, for the next character, we put it in this row, which is correct. Now index is 1, it's not first or last row. So step was still 1. Then we go to this row, this, and now we add the last row, so step -1. Okay, so index is row, and step is, okay, now I see what it's doing. So when we're at the first row, we're gonna increment which row we're gonna go, so we're going to the next row, putting them in there. And now we're at the last row, so we're just gonna go back to the second last row. So now we have index 4, -1, index 3, so row 3. So L3 is gonna append another character. The step is still -1 until we reach the first row again. So step is -1 again. So next round for the next character, it will be index -1. So you'll go to the row above and attach that character, and then attach that, and then attach that. So that is attached, and then we are seeing that, okay, we're at row 0 again. So now instead of step -1, we're doing step 1 again. So we're doing this again. Okay, so brilliant solution. This is like just constructing exactly the structure we need using, so index is which row it is on, and step is trying to guide us to go to the next row, or the previous row, next row, previous row, next row, previous row, until it runs out of all the characters it needs. And then in the end, it simply do a join L. L is this whole thing, and a join L is simply gonna join row by row, each element in each row, and then the next row, the next row, next row. All right. Okay, so I understood from this code, it's really smart. It's completely different from what I'm doing. What I'm doing is like pure math. So, all right. So that's all for this problem. I will look at other solutions later, but I'm pretty happy that I did come up with a solution. And this is really smart. So we'll see you in the next one. And I kind of want to know why people hate this so much. Alright, see you later.